possible ways you can scale are you just get a bigger box. This is kind of limited because you can't keep doing this forever. And that makes it so eventually you're like, well, I hope we don't get any bigger, which isn't really a good way for your company to think. Also, there's a price thing. A small box, I got this from Ask Bjorn Hansen. He did this great MySQL scaling thing. If you just Google for that, it's like the first result. There's a Super Sun box that's like $4 million, and a normal server that's like $3,000. So you can get 1,200 of these servers for the same price as this giant server. So it's much better if you can just get a bunch of little servers and use those. So on the concept of using a lot of little servers, people have tried sharding. But with a relational database, this really kind of doesn't work very well because you're breaking all the relations now. You can't do a join very well. The last way people try is Masterslave replication, which is a pretty good way to do it. If you have a read-heavy application, all the reads can go to the slaves, and then you have one write machine, and then the write machine will replicate the new data onto the slaves. This is good for something that's read-heavy, but not so good for something that's write-heavy. And also, there's a single point of failure there. If the write machine goes down, you're kind of SOL. So, depending on how related your data is, you've got all these new options. On the least related side of the spectrum is key-value stores, which are basically like giant hash tables. They're super fast. These are Project Voldemort, which is used by LinkedIn, and it's written in Java. It's got 75 forks on GitHub, which is where the source is, which is huge. Like 75 people have wanted to touch this code, so there must be something cool in there. And there's Tokyo Cabinet, which is supposed to be blazing fast, and it's apparently very popular in Asia. But they're both basically just hash tables, very simple operations, key value. There's like document-oriented DBs, which is what Mongo is. It's also Couch. They've got a really cool replication scheme where they have master-master replication, so you can have things be offline for a long time and then come back and get synced up again. We've got relational databases and Cassandra, which is Facebook wrote, and they switched over some of their stuff to Cassandra, but not all of it. They only are using it for some stuff. It's a column-oriented database, and it's kind of like a relational database, except it just stores the data in different order and organizes it slightly differently. And then graph databases, which are really cool, but I didn't know any examples of production-ready ones. It's like everything is related to everything else, and you can find paths and relationships really easily. So MongoDB. One of our users on Twitter pointed out that his coffee had a MongoDB logo in it, and I thought that that was really cool. So the next time I got coffee, I took a picture. What we were going for here was to make it easier to use. You know, relational databases are 40 years old, so there's some cruft there. We wanted to make it scalable so that web apps could really easily horizontally scale out. We wanted dynamic queries. So you can have sort of the same feel as MySQL, where you can query for anything. It doesn't need an index. You don't need to predetermine what you're querying for. And we wanted to make it fast. Try to get as fast as like memcache even, which, you know, I mean, we can't because it's not in memory, but for a persistent thing, it's pretty fast. And, you know, keep the complexity. You can do really interesting queries, complex stuff with the database. So we've got a lot of information on sharding, documentation stuff online if you want to look up. But here's a basic example of how it works. The client talks to MongoS, which is the sharding server, which routes the request to one of the sharded shards. The shards can be master-slave replicated, and then there's configuration servers on the side. If you want to try it out, follow along, you can download the binary now if you got a laptop. And we've got it for 32 and 64 on all these, and you can just download it, start right up. And a lot of the examples I'll be giving will be in JavaScript, actually, and it comes with a JavaScript shell you can use to try out stuff. The Java driver you can get from GitHub. It's just a jar, put it in your class path. It's com.mongodb. And it is old. It is our oldest driver. It's been being used in production for like a year and a half now. Which, okay, that's not that old, but like, but you know, it was the first one. We built a JavaScript driver on top of it, and then we kind of got rid of the JavaScript driver, and we still have the Java driver. So, it's very stable. It's very production ready. It's really solid. There is some cruft there, though, since it is the oldest. Here I have, in a lot of the slides, I'm going to be doing stuff in JavaScript versus Java, because JavaScript is much simpler to represent key value pairs, which is kind of the base unit of what MongoDB works with. In Java, this is equivalent to that. If you've noticed, Java's a little verbose sometimes. So, I mean, you can see what's going on here. It's basically creating a set of key value pairs and adding X, Y, and ZW to it. But it's easier to see in JavaScript. So you can just connect. This connects to your default, when you start up the database locally, runs a default host, default port, connects to the blog database. You then get a collection, which is analogous to a table. We used collection instead of table because we didn't want to confuse people. It's not like a table. Everything can be a different shape, a different size, and it's kind of like a bag or a bucket. You don't need, it's not a table. One thing to note is there's no setup here. We just create, none of this has talked to the database yet. It's all on the client side. If we queried the database now, it would assume that there was an empty collection and an empty database. If we inserted something, it would create the collection, create the database. So there's no prep here. We can just start coding. To insert something, we're back to JavaScript. This is just key value pairs. You can do this in Java with just strings. And this would be like a blog post with title, author, content, comments. In Java, you can use any sort of list to create an array, and then just insert it into your collection. When we insert the post, if you look at the object afterwards, it has a new field, an underscore ID field. If you print it out, you'll see that it's a 24-digit hexadecimal number. This is because if you're used to MySQL or something, you're used to having an auto-incrementing primary ID. Well, this doesn't work so well in a sharded environment, so we came up with this underscore ID, which is this nice thing. It's like a timestamp, a machine ID, an incrementing field. And it's 12 bytes, and it's pretty much guaranteed to be unique. So it'll do that for you, or you can set your own. Well, like if you have an underscore ID field, we're not going to overwrite it. We have a lot of powerful update functions. If you want to add a new comment, you do this push thing. This is match the ID of the post, and then for that document, you're going to add a new comment to the array. Anything starting with a $sign is kind of a special Mongo command, and so you don't want fields starting with $sign. So if you look at your object afterwards, you see that there's a new object in the comments array. And that's in Java, how you do that. You can see the comment being created here, and then I created the push here and added the comment to it. And then you just do update the ID with the comment. So there's a bunch of magic you can do. We've got all these comparisons, so you can find things that are greater than, less than, equal to, whatever. You can check if a field exists. You can set a field to a new value, take the mod of a field, do where, which I'll get back to later, check if something is in or not in an array, increment fields. You pass something to increment to let it know how much. You can do negative, positive, whatever. And then these are all things for dealing with arrays. So querying. You can do everything is like you pass find, just a normal normal key value pair with the key and the value you want to match. You can also query for nested objects and reach right in and query for those. Here we've got a query you can do by regular expression too. And if you use sort of a simple regular expression, like starts with or ends with or something, it'll actually use indexes for that, so you can do a really fast regex. And in Java, you can use, the regex is just pattern. You can do pattern.compile and then pass that to the database, and it'll do the query for you. So where? Okay, so the database has this built-in SpiderMonkey engine, so you can just pass JavaScript code to the database, and it'll execute it for you. Here we're querying the database, and we want to return everything that has a Y field that is equal to the X field plus the Z field. It'll just replace, for every object in the collection, this with the object. And then if this evaluates to true, it'll return that object as part of the result set. So this will work for things like numbers and strings. It won't work if one of the fields doesn't exist, because then you'll get non-number and it'll all deteriorate. So where doesn't use indexes for obvious reasons. It's executing arbitrary code. So we recommend that you do something like narrow down your query. Here you can search for everyone named Sally, narrow it down to that, then age greater than 18, and then finally you take their interests, sort them, and then if the third one's volleyball, then that result matches. So that'll save some time. So indexing, I've mentioned. You can just do a normal index. The syntax for all this, this is JavaScript, but the syntax is pretty much the same in Java, aside from the object creation, which is uglier. So this is indexing by age ascending. The direction doesn't matter for single indexes, but if you're querying across multiple fields, you can give each one a direction. You can index inner fields, nested objects. And so, yeah. And so once you've found a bunch of things, it returns a database cursor. And then you can iterate through, and it'll easily fetch more results from the database as it needs. So for an example of this, say we want to do paging. We're going to create a database key value pair with timestamp descending for the sort. And then we're going to do a find. It doesn't actually call the database until you try to get a result. So we can tack on some query options before we actually talk to the database. So we're going to add our sort. We can skip whatever result we're on, and then limit it to the number of results we want back. And then when we finally call cursor to array, it'll send the database all of this information and get back a page of results. And yeah, just return a list of database objects. Everything's a database object. So, and you can, database object is just an interface. So if any of your classes implement it, then you can save those classes directly to the database, which is nice. So if you wanted to do something like Twitter, you'd have a very simple ID, which is auto-generated, a username, and then who you're following. And then each tweet would just be an ID, user ID, the actual message, and then when you did it. You can use Java's date for saving dates to the database. So to add someone that you're following, you just use the push again, and just add their ID to the list of IDs that you're following. And then your object would look something like this, with the person that you're following, this ID in the array. And then you can find all of your followers by querying for people who have your ID in their following list. So if they have your ID in their following list, they're following you. So, and then this would return the entire object for each person. But we only really care about username here. So I'm also passing an optional parameter of username, username1, which says just return the username field. You can pass however many fields you want, that you want. The default is it returns all the fields, but sometimes you want to limit it. So that would just return the usernames for each user. OK, so the maximum object size is 4 megs. If you try to get bigger than that, it's not going to store. So how do you store things like YouTube videos or big pictures or music or oops? What you're going to do is break it up into chunks. Mongo does this for you. This is called GridFS. We came up with a standard way across languages to do this, and we break it into 4 megabyte chunks and store each chunk in the database. So each chunk has a file ID that is taken from its file object. They all have the same file ID, and then it has a number, which is just its order as a chunk. And then the file object is like sort of all the metadata about the file, file name and ID, and you can add your own fields to it, so you can add any metadata you want. So to use it, you just import GridFS. You create a new FS by passing it the connection. It has default collections that it uses. You can set your own. And then you create a file from a file name and the file system, just a string or a file. And then you can put whatever metadata you want in. It has the default fields, but you can add your own. And then you can save it to the database. Then when you want to retrieve a file, you find it using, this is find one. It just returns one file from the database. And it puts it into a GridFS file, which is a special file type that we came up with. And then you can write it to the file system. You can get the bytes. You can pretty much do whatever you were going to do normally with a file. So then another good application for Mongo is logging. You can use it for logging, and it works really well. That's because inserts, updates, and removes are really fast. You can you send things to the database, and the driver just keeps doing what it was doing before. They don't acknowledge the insert. You can actually, so it's sort of like a send and throw away. So it's not safe, which is one of the reasons you can do it fast for logging, because you probably don't care what you're inserting. But if you want to make sure it got in there, you can make sure that there was no error sending it. You can actually do a sort of, use the SpiderMonkey to send a bunch of JavaScript to the database to do it all atomically for an insert, and you can end up doing it really safely. But for something like logging, where you probably don't care much, you can just send and forget, and it'll be almost instantaneous. Then we have these things called cap collections, where if you're worried about like logs, if you keep logs in databases and you're worried about them growing to be like 50 gigabytes or something, you can do these cap collections, and you can set, okay, I just want this collection to only be able to grow to be 2 gigabytes. And then as it gets full, the oldest things will drop off the end, and then new things will be inserted, and it'll stay at 2 gigs. And you can also set max number of elements and stuff. So, and then we have these things called upserts, which are like updates, but if the object doesn't exist yet, it inserts it. So that can be handy for, you don't have to prime your database with whatever kind of object you think you want. You can just do an update, set upsert to be true, and it'll insert the thing instead of updating it. And then you can use increment for counts. If you're using page analytics or something, you want to record every page view, you can send to the database an increment in the update, and it'll increment for every page view. And that's actually all I had. I'm sorry. So yeah, if you want to contact me, contact MongoDB through Twitter, or everyone's always hanging out on IRC. And there's our website. There's a lot more documentation on the website. And that's about it. Are there any questions? Yes, the question was, what consistency model do we use? And we use eventual consistency. The database will eventually replicate to all the shards, but we figure most of the databases for web applications figure that you'd rather not find out that your friend is eating bologna, like the second that he posts that, than have the whole site be down. So yeah, we just, yes. What is the sweet spot for creating an application with this? How would you divide labor between this and a relational database? I'd say that this is really good if you're making a web application, basically. I mean, like, it's, because of being fast and scalable, it's, that was what it was made for, basically. With a lot of our users, they are dividing it into two parts, and they're still going to use SQL for some stuff, and then they start using this, and then they find out it's really easy, and they end up using it for their entire application. But I think that it's good. It's good when you don't have transactions. It's good if you don't have something like a shopping cart. If you're having people buy something, you probably want something with transactions. If you have a lot of relationships, you don't want this because, I mean, you can link documents together, but it's not what it's strongest at. Yes? The question is, how do you do reports with it? And right now, we have some simple, like, group by counting, aggregation stuff. We're planning on adding a MapReduce layer. We're planning on adding more complicated aggregation stuff. If people are interested, they should go on the website or the user list and request it. Like, things that are popular we'll implement first. So if people are interested. Yes? It should basically scale unlimited if you're using sharding. Do we have data for read and write performance throughput rates? We've got performance testing on the website. It varies on the driver, but it's I can't remember the numbers off the top of my head. If there's internet, I can look it up. But if you go to performance testing on the website, you can see it's very fast. I don't know the exact numbers for like throughput. I know people are using the sharding in production, but yeah. Yes. Well, SourceForge is probably the most major. They switched over all their projects and the project pages to it. Sorry, I see you back there. I'll get you. Yeah, and Mozilla Ubiquity is using it. There's this company called Discus. They do a bunch of server stuff with it, like a lot of analytics. There's Business Insight. I'm not sure. We've got a list on the website. If you look up production deployments on the website, there's quite a few people using it for various things. Why is Mongo different than CouchDB, and why would I choose Mongo over Couch? So CouchDB has this thing called views, where you have to come up with your query beforehand and then create a MapReduce function for it. Whereas MongoDB, you can do whatever query you want on the fly. You create your own indexes, so it's a little more flexible. If you also, it's a little easier to use a lot of times for people conceptually because they have a hard time wrapping their head around using MapReduce for everything. I don't know, I don't want to badmouth anyone, but like it seems like it's a bit faster. MongoDB is, we made a lot of choices to make it fast. CouchDB on the most basic level, I mean, it goes over HTTP for everything. The socket is just going to be faster than that. Yes? Not yet for Java, I believe. For some of the other languages, people, other people have done them. We're just kind of taking care of the basic drivers here. If people are interested in doing them, there's a lot of examples out there in Ruby, Python, PHP, because it's definitely something people like doing is being able to put in and take out objects of a certain type. So, yes? Is there anything like show query? Yeah, there's the cursor has an explain method. It'll give you all sorts of details about what the database is doing, how long it took. You can also run the database in a verbose mode that'll tell you every little thing it's doing. So you could keep track of the database logs if you wanted. Is there anyone else? Okay. Thank you very much.